Hey, John here. Let's define something that we call a binary search tree. Oftentimes you'll see it abbreviated as BST. So a binary search tree is just a binary tree with certain properties, two simple properties. One, each node has a key value, and that key value must be greater than all the keys that are found in its left subtree. And it has to also be less than all the keys in the right subtree. In other words, the tree is sorted. We say it's sorted in order. And we say that because if you traverse this tree using an in-order traversal, you will have visited all the nodes from the smallest to the largest key value in order. Okay? The other rule is that all subtrees must meet the same criteria above. So let's zoom in a little bit here. Look at these trees. This one on the left is a binary search tree, okay? This one on the right is not a binary search tree. So let's see what the differences are. Any node in this tree on the left, like this one here, the root, has key. This one happens to be 6. Is the key of every node in the left subtree over here of 6 less than 6? Yes, it is. All right. Is every node in the right subtree greater than 6? Yes, it is. Okay. Now we have to recursively ask the same question. Well, what about this node here with a 2 in it? Is every node that's in the left child subtree of 2 over here less than 2? Yeah, you can see that's true. Well, are all the nodes over here in the right subtree of 2 have greater than keys that are greater than 2? Well, yes, it is. Okay? And we have to ask about this subtree over here. Does this subtree have keys in its left subtree such that they're all less than 4? Yes. Does the keys in the right subtree have keys that are greater than 4? Well, it doesn't have one, so we don't have to care about that, right? Well, the same cannot be said about this tree here. You can clearly see there's a 7 hiding down here that was added. And you can also realize that 7 is greater than 6. Therefore, this cannot be a binary search tree. Now, given a tree with that structure and sorted in order, we can make certain observations. We know that to find any node in that tree is going to take log n times, on the order of log n comparisons. We're going to simply follow a path down from the root in order to find the nodes that we're looking for. Okay? What does it mean to traverse every node from the smallest to the largest key? Well, we can traverse the tree using an in-order traversal and execute it in order n time. So what does it mean to find the node with the smallest key value? You simply traverse the path down to the leftmost child of the root, and you'll get there in order log n time. The same thing's true about finding the node with the largest possible key. You start at the root and go down the right path, and you'll find the node with the largest key in order log n time. What about to delete and insert? As you'll see, deletion and insertion requires you to do a search to find the node or the position where you want to insert a node. Then you can attach the node at that location. So since search takes order log n, that is the time it takes to figure out where the thing is going to go. And then in order 1 time after that, you'll see we can do the insertion or deletion. So let's start with an empty tree and go through the process of creating a binary search tree by simply inserting elements with the given keys in this example here, all right? So what we know is that if the tree itself is completely empty and you want to insert a new node into the tree, there's only one place for it to go. It becomes the root. So if we want to insert new nodes whose keys have these values in the order shown here, 3, 6, 5, 1, 2, and 7, into an empty tree, you'll end up with a tree that evolves as we're drawing it here. So what do? You say the tree is empty, therefore 3 becomes the root. It's the only element there. That's the only place it can go. If you then want to insert a 6, well, what you do is you come in and you ask, is 6 less than the key of the root. Is 6 less than 3? No. Okay, it can't go on the left. It must go on the right. Therefore, you create a new node and you put the key in there and you make it the right child of the root. If you then insert a 5, you'd use the same process. You say, is 5 less than 3? No. It must be the right. It must become part of the right subtree. So you find that you have a right child of the root. You go and ask the same question. Is 5 less than 6? Yes. It must be connected to the left subtree of 6. Well, before you insert 5, there isn't one. Therefore, 5 becomes what we could call as the root of the left subtree of 6. Okay? If you then want to insert a 1 at this point, you're going to come in here and you're going to say, is 1 less than 3? And the answer will say yes. It has to go in the left subtree of 3. You'll notice there isn't one there, and you end up with a tree that looks like this. The 1 becomes the root of what would be the left subtree of the root node with 3. If you then want to insert a key with a value of 2, you're going to see it's going to go down here, right? Why? Because you're going to start at the root, and you're going to say, is 2 less than 3? Yes. You're going to go to the left subtree, and you're going to say, is 2 less than 1? No. Is it greater than 1? Yes. Therefore, go to the right subtree of 1 that's not yet populated. Therefore, 2 becomes the root of the right subtree of this element with a key of 1 right there, okay? If you then insert what? A 7, the last node over here. Start at the top. Is 7 less than 3? No. Is it greater than 3? Yes. Go over here. Is it less than 6? No. Greater than 6? Yes. Is there a subtree over there? Not yet. Therefore, 7 becomes the root node of what would be the right subtree of 6. All right? That's how you fill in a binary search tree. You could write an algorithm to do this, quite straightforward. It's simply a loop that's, as you can see, it's traversing this path in the same way you would traverse it to locate something that's in the tree, right? What if you had this tree, it's all filled out, right? And you want to say, I want to find the node whose key value is at 2. Well, you start at the root. Is this node key equal to 2? No. Is it less than the key? Yes. Go to the left subtree. Is this equal to the key we're looking for? No. Is the key we're looking for less than 1? No. Then you go to the right subtree and ask, is this the key I'm looking for? Yes, it is. You found it. So you can see that part of the process of inserting a new node into a binary search tree is effectively searching for where it would be if it was already there. And we do this by simply traversing this path using the simple logic, is it greater than the current key or less than? And you use that logic to traverse to the subtree of interest there, okay? And when you're inserting, you'll find out eventually you'll run into a dead end, and that's the place where you put the new node. Now, it's quite often that you'll find a data structure that has all unique keys, and that's great. Keeps things nice and simple. But what if that's not the case? What if you have to deal with the fact that you have, a data structure of some kind that requires elements that have the same key? You have to have duplicate keys, right? Well, one way to deal with this might be if you just need to take note that there were 5 of something, you can put a count field in the node object and just keep track of how many were inserted. Another way to do it, if the node is a complex thing, right, and just knowing that there were 5 doesn't really help you because they might all have the same key but with different values, right? In that case, you could put a container in the node itself, like, put a list in there or a vector or something like that. So you could create a node that has a key, and then the value for that key could itself be an entire list of values or a vector of values or something like that. Another way to do it would be to literally just create nodes for every one of those duplicate keys. And then just create a rule that says if there's ever a duplicate key that needs to be inserted into my binary search tree, it'll always go on the left. Otherwise, you won't know how to find it later on, right? And if you do this sort of thing, you also then have to ask yourself the question, what happens when you say, give me the value of some key, or give me a node with this key, you're going to have to think about the, the programming interface to this data structure. Do you need a get all or a remove all? These might return, an iterator range or something like that. I'm saying, here's all the 3s, or here's all the 7s, or maybe I want to remove all the nodes who have a key equal to 12, or something like that, all right? So you're going to have to think about all this stuff if you run into a situation when you have a data structure that has elements with duplicate key values. So inserting a node into a tree is relatively straightforward. It amounts to finding a place where it belongs and then just attaching it to your tree. But what if we want to delete nodes? Well, we have 3 different cases that we have to deal with, right? What if we delete a leaf node, one with no children, a node with only 1 child, or a node that has 2 children? 3 different cases. In all cases, we have to make sure that when we're done deleting, that we preserve the property of the binary search tree, and that is that it remains sorted so that an in-order traversal will visit all the nodes in sorted order. So let's look at the first case. What if we deleted a leaf node, a node with no children here, right? So in this example, we're deleting node 45 over here, okay? First thing we need to do is find it. Well, 45 less than 25? No. Is it greater than 45? Yes. Then we follow down here using our greater than, less than logic here. You can see that's what's going on over here. So we then locate the node that we want to delete. We see that it has no children at all. This is the easy case. You just prune this pointer off. As you can see here, just change the pointer to it to null, and then delete it. Not a problem. What if we want to delete a node that only has 1 child? Well, that's kind of simple. If we want to delete a node whose key is 20, we first find it. It's less than 25, greater than 15. Oh, found it, right? What do? Well, you go to the parent of the node you want to delete, and you simply hook it to the 1 child of the node you want to get rid of, as you can see over here. So if I want to delete 20, and 15's right child is 20, and 20's left is 18, or if its right node was 30 or something over here, of course it would have to be less than 25. It could be like 21 would be over here. It doesn't. My point is, it doesn't matter whether we're dealing with the left child or the right child of the node to be deleted. If and only if it has 1 child, what you do is you go to the parent of the node to be deleted and just set its pointer to that 1 child. Then you will have unhooked this node and you can just simply delete it. Now, what if we want to delete a node that has 2 children nodes? Well, first let's define some terminology. A successor, okay? In the simplest of terms, the successor of any node, X, is another node that has the smallest key greater than that of X. It is, in other words, the node that will come next if you're doing an in-order traversal. Now, the mechanics of finding it depend on these 2 observations right here. Well, if the node X is a right subtree, then the successor of X is going to be the leftmost element in that right subtree. For example, what's the successor of 15 here? Okay. Well, it's the leftmost element in the right subtree. And by that we mean you go right once and then you go left as far as you can. That's 17 right here, okay? What's the successor then of 7 here? Same thing. You go right once and left as far as you can. And when there's no more left, that's the one right there, 9. What's the successor then of 13? Well, that doesn't work. There is no right subtree, so you do the rule down here. The successor of 13 here, it's the lowest ancestor of X, which is 13, that's above X on the path to the root that has X in its left subtree. You might have to read that 2 or 3 times, okay? But take a step back here, right? We're deleting 13, right? We want to know its successor. we have to find the closest relative for which this node here is in its left subtree. All right, well, we know that 13 is in the right subtree of 7, which is in the right subtree of 6, which is in the left subtree of 15. Therefore, 15 is the successor of 13. Predecessor, it's exact opposite. Which one comes before in search order rather than after, okay? It's the largest key smaller than that of X. And you'll notice it's a mirror image, right? So if X has a left subtree, the predecessor is therefore the rightmost element of the left subtree, which is the exact opposite of what we saw up here. If it is a right subtree, then it's the leftmost of the right. And just like before, what if there is no left subtree, right? Well, then you go find the nearest ancestor above the level of the key such that X is in the right subtree rather than the left as it was in the previous case. So what do we say? What's the predecessor of 6? Well, if 6 is here and we have a left subtree, then it's the rightmost element in the left subtree. And when we talk about rightmost, just like before, what we're really talking about doing is going left once, and only once, and then follow this chain to the right as far as it goes. Okay? In other words, don't think about how it looks to you visually. All right? For example, let's say there's a tree underneath 2 here that has 1,000 elements in it. And this tree becomes extremely wide. It's not the one that's visually to the right over here, okay? It's the one that is furthest to the right at the top level of the subtree that you're inspecting here, right? So you're going to go left once and then right many, many, many times, and not just left, right, and look all over the place, okay? So the predecessor of 6 is 4. When the tree is small enough, you can do a visual check and figure it out in your head. What comes before 6? Well, obviously, it's 4, okay? Then what's the predecessor of 15, right? Well, if you want to know what comes before 15, when we have a left subtree, it's left once, right as far as you can go until you run out. Well, that's 13 here, okay? Again, you can check that by visually scanning the whole tree to double check your work. What's the predecessor of 17, okay? This is one that doesn't have a left subtree. So you have to go back up towards the root and ask yourself, is 17 in the right subtree of each node as you move back towards the root? And the answer here would be no, because 17 is in the left subtree of 8, okay? Go to the parent of that one. Is 17 in the right subtree of 15? Well, yes, it is. So it turns out that 15 here is the predecessor of 17. Now, with those terms in mind, we can now discuss what it means to delete a node that has 2 children. Well, it turns out that if you're going to delete a node out of the tree and you want to maintain the sorting order, to support the rules, to keep it as a binary search tree. If you want to delete this node right here, what do? We can't just kind of like hook 20 up over here and leave that linked in there, because we would lose all this. We still have to keep this tree structure intact. Well, the rule is you can either find the successor or predecessor of the node you want to get rid of, and then you can actually swap it. So let's say we want to, you can pick either one. It doesn't matter. The algorithm works either way. So in this example, we're going to choose the predecessor. What we do is we swap these 2 values. If I want to delete 15, find its predecessor. Okay, left and then as far right as you can go. There it is. Now swap these 2 nodes. 9 will become up here. The tree will still be in sorted order, but there'll be this illegal node down here. But by definition, remember that the predecessor of 15 is going to have no right child over here. Therefore, once you've swapped these, you just go use the algorithm for deleting a node with a single child. Okay, done. You don't actually have to do it when there's two. You swap it and then get rid of it when there's a single child. All right, so that's what you can see over here. You see 9 and 15 have been swapped. And then once you've got this, you can just say delete the node with a single child using that algorithm. Now, if it's not completely obvious to you, let's go back up and look at these trees again up here. Anytime you have a node with two children, both the predecessor and the successor to this node will always be in one of its subtrees. And whenever you find the predecessor or the successor in one of its subtrees, you'll always find that predecessor in this example, of 6 would be 4 over here, will always be a node that has at most one child. Because, right, there could be a 3.5 over here, but there couldn't be a 5. Okay? If there was a 5, then the 5 would be the predecessor of 6. All right? My point is, in the delete case, when you have two children, the predecessor will be in this left subtree over here. The successor will be in the right subtree over here. In every single case, the predecessor, if it's in a subtree, will have 0 or 1 children. And if the successor is in this tree over here, it'll have 0 or 1 children. Work out all the possible cases, you'll find that that is true. And that therefore, whenever you need to delete a node from a binary search tree that has 2 children, this approach will work. The predecessor will have at most 1 child. The successor of 15, in this case it would be 18, has at most 1 child. In this case it has 0. In other words, you can always play this swapping trick followed by deleting a node that does not have 2 children. So that's the definition of what a binary search tree is, how you use it to find things, how you can insert new elements into such a tree, and how to delete elements out of it in the 3 cases that we have to concern ourselves with. Thanks for watching.